Hello and welcome. This is Valerio, and in this video I would like to help you setting everything you need in order to run the experiment described in the blog post Greener Machine Learning Computing with Intel AI Acceleration. After this video, I hope you will get a sense of how scikit-learn Intellects works. Scikit-learn Intellects is the Intel optimized version of scikit-learn, so that you can start doing greener machine learning computing yourself. On the left hand side of the screen you can see the main page of the GitHub repository attached to the blog post. You can find this repository on at github.com/anaconda/intel-green-ai. The repository contains everything you need to run the experiments and a README file including all the instructions step by step. You can follow these instructions at your own pace, or you can watch the video and do this with me live at the same time. On the right hand side we will be using a terminal window where we execute all the commands. I'm running on a Linux machine because the Linux machine and the Linux operating system is what I use originally when I run the experiment. I'm using Ubuntu operating system, and in particular the Ubuntu 20.04 version. Before we start, there is an important step we need to make sure in order to use Intel optimized version of scikit-learn. If you look at the documentation linked in the guide on the repository, you can see the system requirements for Intellects, scikit-learn Intellects. In particular, we have to make sure that regardless of the operating system and the Python version we're running, we have to make sure that the CPU of our machine supports at least one of these instruction sets. I've attached a couple of commands you can run on Linux or macOS, depending of your operating system of course, to check your local machine configuration. Since I'm running a Linux, I'm going to try the first one and show you that ls CPU, and then looking for specific information in the set that we return, and in particular we're looking for ss2 or ABX. As you can see on this machine we have everything we need, so we're good to go and we're ready to get started. To do that, the very first step is getting this repository on our machine. We can either download it directly on from GitHub, or we can clone it. I'm going to demonstrate how to do it using git clone. So we copy the HTTPS URL of the repository here, and then in the terminal window, git clone, and we copy. This has created a new Intel Green AI folder on our machine. We can navigate into the folder and get everything we have on the original repository. Once we are here, now we're ready to start with the first step, and the first step we have to do is to setting up the Conda environment. In order to set up the Conda environment, first we need to make sure that we have Anaconda Python distribution installed on our machine, so that the Conda command is recognized by our operating system. If that's not the case, the guide contains a link to the download page on the Anaconda website that you can navigate in order to download the Anaconda Python distribution you need depending on your operating system. I've already installed Anaconda on this machine, so we can skip to this step and go directly to creating the actual environment. The repository contains an environment.yaml file, which is a file that you can use with Conda to immediately recreate the environment you need, including all the dependencies and all the packages you will need to run the experiments. To do so, we have to run the command conda m create -f option and passing the environment.yaml file to this command. This will download, looking at the dependencies, download all the packages and install everything. Depending on your internet connection in your machine, this may take a few seconds or a few minutes. In the meantime this completes, we can have a look at the environment.yaml file and see what are the actual dependencies included in this repository. As you can see, the list of packages is not that long, it's very short. And it's important to highlight that we have Python 3.10 that we'll be using, scikit-learn 1.1 version, and scikit-learn Intellex 2023 version. The other packages here are just dependencies, and more importantly, TQGM is used for download data sets. Pandas is a specific dependency for the experiment, and OpenPyXL is a very is an open source package used to generate Excel version of the report after the benchmark has been run. In the meantime, all the packages have been installed here, so we're ready to go activating our new green AI Conda environment. We can do Conda activate green AI, and now we are within the environment, as you can also see in the terminal, and so we're good to go. From now on, whenever you're going to install or run any Python command, we will be running within the green AI environment. Brilliant. Now that we have the Conda environment set up and available, the next step is to download the code and the data. As for the code, we will be using the machine learning benchmark available at the Intel Python GitHub repository. We can have a quick look at this benchmark. This benchmark is indeed brilliant. It contains everything we need to run the experiment. We don't have to write a single line of code. We just have to use it. This benchmark works via configuration files in JSON format, and the configuration files I've used to run the experiments are included in the experiments folder in the repository. We can have a quick look at this folder, and it contains all the JSON files needed to run the different experiments described in the blog post. Please refer to the blog post for additional details of each of these experiments. You can have a quick short description in this table here as well. To download the machine learning benchmark code I used for the experiment, I specifically tagged and forked the repository into a specific version, and this is mainly for reproducibility purposes. From a reproducibility perspective, this is paramount important because we're freezing the status of the code I use to run the experiment, so we're absolutely sure that when you're running the same code on your machine, you're using exactly the same version of the code that I used when I ran the experiment. I can copy the command here in order to download the code, and I will be explaining what's going on. So I'm cloning the benchmark code called scikit-learn bench from this repository here, and I'm creating at this particular branch and creating everything and downloading everything into a green AI benchmark folder. So we run this, and now we have a new green AI benchmark included in our folder. Now that we have downloaded the code, the next step is to download the actual data. This procedure may take several minutes to complete. It depends on your interconnectivity, but most of all, we will require to download around 18 gigabytes of data from the internet. So this may take some time. For this reason, especially if you're running the command on a remote machine, as I'm doing, I would recommend running the download within a tmux session. Tmux is a specific command you can run on Mac or Linux to create a new terminal session that can be detached, which means that you can leave it be, you can leave it there running, and even if you get disconnected from the machine, the command still runs on the server. So you can go back and see you can reconnect to the session and have a look at how the download is proceeding. In order to do this, I will run tmux new -s to create a new session. We will give a name to the session, say download_data. You can tell we are within tmux because a new green bar has appeared on the terminal. And since this is a new terminal session, completely detached from the previous one we were running, now we have to reactivate the Conda Green AI environment. So Conda activate Green AI first, and then we can proceed on downloading the data. I copy the command again from the guide and then explain what this command will do. I paste it. Okay, the first thing is we will be moving within the benchmark folder created in the first step, so the Green AI benchmark. Now that we're within this folder, we will be running this load dataset script. And this is another reason why I specifically indicated the tagged version of the benchmark in the previous step, because this is an extra script included in this specific version, not included yet into the official benchmark version. It's part of a pull request, to be honest. And this script contains all the automation needed to download everything. In particular, this script included in the datasets package of the benchmark is called load datasets. It relies on an environment variable called datasets root, and this environment variable is needed to specify the path to the folder where all the datasets should be downloaded. In particular, it's a data folder within the benchmark folder. This folder doesn't exist, the script will create this folder for us. And the last option added to the script is --configs. This option is specifically used to pass in a series of benchmark configuration files, including the reference to a specific dataset needed to run these experiments. We'll be using the skl public config JSON, which is the overall benchmark experiment we run for the Green AI machine learning computing experiments. This contains everything we need, and so all the information of the dataset we will ever need to run everything in this particular set of experiments. The idea behind this option is I have a specific configuration. I want to download the dataset beforehand, as we want to do, so that when we run the experiment, the data will be there, and so we won't waste time into downloading the data, and so having an extra overhead when we calculate the energy consumed by the experiment. So we run this. This will script has found that we need 25 datasets to download, and it will take some time. So we can leave this be and proceed with the next steps. Once the data is downloading, the next step is to enable the measurement of the energy consumed by any program on our operating system. In order to do so, to measure the energy consumed by programs, we'll be relying on a technology which is available since 2010 on every Intel CPU. This technology is called RAPL, as in running average power limit. Unfortunately though, sometimes this is not automatically enabled on the operating system. So what we need to do is to enable the operating system to have access to this information directly, so that we can read this information directly from the sensors and collect this when we run our machine learning experiments. To do so, I'm going to demonstrate how to install and enable everything on Linux Ubuntu system. And it's important now to highlight that in order for you to proceed, you need to have sudo or root permissions. If that's not the case, unfortunately, there's much you can do on this regard. You have to ask directly to your system administrator to do so. So the first thing is to install some extra modules on the kernel. To do so, the command is sudo apt install Linux modules extra, and then we get the version specific of our kernel. This is downloading, installing, and configuring the modules within the kernel we're running. Once this is complete, the next thing is looking at all the modules in the kernel extras list, including the name RAPL, and probing or loading this module dynamically into the kernel so that we can finally enable. The overall thing is not entirely complicated. It's just like a bit cumbersome and contains different steps involved. Meantime, everything has been installed, so we can look at the modules we need to probe into the kernel. We can copy this command here directly. This feature of GitHub is very handy. So we find in the modules folder everything which contains RAPL in its name. You should have something similar to this. Processor terminal RAPL, Intel RAPL MSR, Intel RAPL common, RAPL.ko. So one by one, we're going to probe dynamically this module into the kernel by running sudo mod probe and the name of the module. Mod probe and the name of the module without the .ko extension. So mod probe RAPL, sudo mod probe Intel underscore RAPL underscore common, sudo mod probe, apologies, Intel RAPL underscore MSR, sudo mod probe processor underscore thermal underscore RAPL. There you go. Now, in order to check that everything has gone well, we list the devices included into the sysclass PowerCap folder. So we do ls/sys/class/PowerCap. Perfect. We have everything we need. So now we have access to the Intel RAPL devices here. And this means that everything is set up and ready to go to measure the energy consumption using RAPL directly. Perfect. Now that we have enabled the RAPL technology on the operating system, what we need now is a program to actually read from the sensors and return the energy consumed by the program. To do so, I've used JOWL-AT, which is a very simple and yet very powerful script that can be used to monitor the energy consumed by any program you run on your operating system. JOWL-AT will read from the Intel RAPL devices enabled in the previous step using the PowerCap framework on Linux, and then it reports back the amount of energy in joule consumed on the specific devices the script supports. In our machine, in our specific configuration, we'll be having CPU and memory. In case you will have GPU, JOWL-AT can also monitor GPU integrated on the CPU. But this is not going to be the case, so we'll be focusing on CPU and main RAM. In order to get JOWL-AT, all we need to do is to clone the repository of the project. It's an open source project, so we're still on the free and open source software in this particular experiment. So we copy the URL of the JOWL-AT. You can clone the JOWL-AT folder wherever you prefer. I'm going to do this within the Intel Green AI to keep everything contained, but you can clone this whatever you prefer. So I'm going to clone this, and this will create a new JOWL-AT folder. If we navigate into this folder, we will see that we have the JOWL-AT.sh, which is the actual JOWL-AT program we'll be running. In order to check that everything is working with JOWL-AT, we can run this JOWL-AT script with a -L option. This is just to be used to show which is the information that JOWL-AT has access to. So for every program you run, JOWL-AT can give you the amount of energy consumed in joule on the CPU, the DRAM, the duration, so the amount of time elapsed, and the exit code, so whether the program exited with a success code or an error code. Great, now that we have everything set up, all it's needed to do is to finally prepare us to run the experiments of the benchmark. And so it's finally the time to explore what's included in the runners folder in the repository. The runners folder contains a series of scripts that have been specifically prepared for you to make to run specific sets of experiments easily, also using JAWL-AT. So each of these scripts has a similar naming pattern. They all have an ending which could be Intel opt-off or Intel opt-on, depending whether we're using or not the Intel optimized version of scikit-learn. And then there's a one script specific for each experiment considered. So we have the classification, task experiment, clustering, domain introduction, regression, the whole benchmark using all the publicly available dataset, and the support vector machine, SVC, Intel opt, off, and on. We can have a quick look at each of these. So the script, what it does is to make sure that the benchmark results folder exists, and then it runs the benchmark code. In this particular case, we don't want the Intel optimization activated, so we pass an extra option, no Intel optimized. Then we pass in the configuration file we want to run. In this case, it's classification.json, included in the experiments folder. And then we also set up where we want to save the actual results of the benchmark. And so a new classification underscore opt-off.json will be created, finally converted into an Excel report automatically by the benchmark code. If we have a look at the same script with Intel optimized version, the output is very, very similar. The only difference is that this time the not Intel optimization, of course, is not provided. And the name of the result file will be different. Instead of being classification opt-off, will be classification opt-on. So the runners folder contains all the script already prepared. And the reason why we have this as a shell script is mostly to allow an easy use with JAWL-AT directly. So all you have to do is to run JAWL-AT and then the script you want to run in order to run the experiment and at the same time monitor the energy consumed using JAWL-AT. So in order to get prepared for this, we have to move these files directly into the benchmark folder, in particular the Green AI benchmark we created previously. The reason why we do this is because we make sure that every dependency and all the paths are essentially available, and so we won't incur in any error or issue during the execution. So the first thing to do, now we are in the Intel Green AI folder. So the first thing to do is to copy the experiments folder within the Green AI benchmark folder. To do so, we do cp -r, which is the minor recursive, which means copy everything recursively, included into the experiments folder, into the Green AI benchmark folder. The second is to copy all the runner script into the same Green AI benchmark folder. So cp runners / run underscore star, which means all the files that starts with run underscore will be moved and copied into the Green AI benchmark folder. Now if we navigate the Green AI benchmark folder, we should see an experiment folder containing our experiments. There you go. And all the scripts have been moved here, ready to be executed. The last step is to run JAWL-AT and then the as instructed here, and then the script we want to run for the specific experiment. As an example, we can now run one of these runner scripts using JAWL-AT to measure the energy consumption. First, we have to make sure that the download of the data has been completed, so we can reconnect back to the tmux session we had left running before. We can list the available tmux session using tmux ls. We have the download data session still available, so we can connect to that session doing tmux a -d and the name of the session, download underscore data. As you can see, everything has been downloaded. All the 25 data sets have been downloaded. So this has been complete. We can even close this session by running exit. And now creating a new session to run a specific experiment. So we do 2max new -s. And now we can create a session and we can name it as we prefer. So for example, let's say we want to run the first one, run the classification intel opt off. So let's create a new session for the classification task. We'll be running presumably first the known optimized version of the benchmark and then the optimized version of the benchmark. So 2max new -s classification. We have, again, since this is a new session, we're going to reactivate the Conda environment we need, the green AI Conda environment. Now, we are within the same folder we were before, so it's like green AI benchmark folder. And so we can now run this, let's say this script. So the jowl.at script lives in the parent folder. So we go like /jowl.at, jowl.at.sh, and then the /run _classification intel opt off.sh. We hit return, and this will automatically run the script for us. There won't be any output till the very end where we get the output of the jowl.at with a table of the energy consumed. So now we can detach this session, similar to Control B and then D keyboard shortcut, and we can do htop, for example, or simply top to have a look at the process running. As you can see, we have a Python sklearn logistic regression non-Intel optimize running here. So everything is running. Now all you have to do is wait and get the result in the end. As an example, we can now run one of these runner scripts using jowl.at to measure the energy consumption. First, we have to make sure that the download of the data has been completed. So we can reconnect back to the tmux session we had left running before. We can list the available tmux session using tmux ls. We have the download data session still available, so we can connect to that session doing tmux a -d and the name of the session, download _data. As you can see, everything has been downloaded. All the 25 data sets have been downloaded, so this has been complete. We can even close this session by running exit, and now creating a new session to run a specific experiment. So we do 2max new -s, and now we can create a session and we can name it as we prefer. So for example, let's say we want to run the first one, run the classification intel opt off. So let's create a new session for the classification task. We'll be running presumably first the known optimized version of the benchmark and then the optimized version of the benchmark. So 2max new -s classification. We have, again, since this is a new session, we're going to reactivate the Conda environment we need, the green AI Conda environment. Now, we are within the same folder we were before, so it's like green AI benchmark folder. And so we can now run this, let's say this script. So the jowl.at script lives in the parent folder. So we go like dot dot slash jowl80 jowl80.sh, and then the dot slash run underscore classification interlocked off dot sh. We hit return, and this will automatically run the script for us. There won't be any output till the very end, where we get the output of the jowl80 with a table of the energy consumed. So now we can detach this session, similar to Control B and then D keyboard shortcut, and we can do htop, for example, or simply top, to have a look at the process running. As you can see, we have a Python sklearn logistic regression non-Intel optimize running here. So everything is running. Now all you have to do is wait and get the result in the end.